friends, welcome to this lecture. In this lecture we will discuss the method of green functions to solve the non-homogeneous boundary value problem with the help of Green's function. So, first of all we should discuss the what is green function and what are the properties of green function and how to construct the green function, and then with the help of green function how we can solve the how we can handle the non-homogeneous boundary value problem. In some case we can get the solution in closed form, and in some cases we will get the solution in terms of say some kind of equation which is known as integral equation. So, we will consider all these things in this lecture and the lecture afterwards. So, first let us start the first theorem, that is that the homogeneous problem, that is P naught x y double dash plus P 1 x y dash plus P 2 x y equal to 0, along with the two boundary condition L 1 y, that is A naught y alpha plus A 1 y dash alpha plus B naught y beta plus B 1 y dash beta is equal to 0. So, here we have a homogeneous equation with the two set of boundary conditions, and here we are assuming that this L 1 and L 2 are not linearly dependent boundary conditions. So, it means that this A naught A 1 B naught B 1 is not a scalar multiple of C naught C 1 D naught and D 1. And here we assume that this homogeneous problem along with the boundary conditions has a trivial solution. Then green function exists for this set of equation, and there exists a unique solution for the non-homogeneous problem P naught x y double dash plus P 1 x y dash plus P 2 x y equal to R x with these homogeneous boundary conditions. So, idea is that here we have homogeneous equation along with the boundary homogeneous boundary condition, and if this has trivial solution then green function exists, and with the help of green function we can find out a unique solution of the non-homogeneous problem this along with the boundary condition, and the unique solution is given by the following formula, that is yp equal to alpha to beta g of x t r t dt. Here alpha beta is the interval in which we are finding the solution. So, it means that your homogeneous problem is given in terms of this alpha and beta here. So, here I am denoting the unknown function is y, and it is a function of x, and x is lying between alpha and beta. So, here we will try to prove this later on, but first we discuss the property of this kernel of this equation. So, here yp equal to alpha to beta gxt rt dt. So, if we know this function gxt which is known as green functions for the problem 35 and 36. So, if we know the green function, then we can find out the solution of the non-homogeneous problem, that is going to be unique. So, let us first discuss the properties of green functions. So, here there are some properties of green function. First property is that gxt is continuous in alpha beta cross alpha beta. So, here x is in alpha beta and t is in alpha beta. So, gxt is continuous in this rectangle. Now, dever g by dever x is continuous in each of the triangles, that is x less than or equal to t and t greater than or equal to x, and alpha less than or equal to t less than or equal to x less than or equal to beta. So, it means that it is basically continuous in each of the triangles, and it also at the diagonal term, let me write it here, this is say alpha beta and this is alpha beta here. So, here we have this, and then we have the triangles here. So, we have two triangles. So, in each of the triangles you can say that your dever g by dever x is continuous, and at the say diagonal term they have jump discontinuity, that is dever g by dever x t plus comma t minus dever g by dever x t minus comma t is equal to 1 upon P naught t. So, here we discuss the properties of green function. So, first property is that GXT is continuous in this rectangle alpha beta to cross alpha beta. So, here let us say that here we have this axis which represent the x and this represent the t here. So, x is from alpha beta and t is also from alpha beta. So, we are writing it here. So, it is somewhere here. So, x axis and t here. So, this represent alpha and this represent your beta. So, now what is given here that in this whole rectangle your GXT is continuous, and also second property is that double g by double x is continuous in each of the triangles. The first triangle is alpha less than or equal to x less than or equal to t, that is this here. So, here double g by double x is continuous in this triangle and also in this triangle, that is alpha less than or equal to t less than or equal to x. So, here your this in this region your double g by double x is continuous, and when we look at the diagonal term of this triangle, then rectangle, then we have this jump discontinuity, means in each of the separate region double g by double x is continuous, but at the diagonal it has a jump discontinuity, and jump discontinuity is given by this quantity 1 upon p naught t. So, it is given by double g by double x from t plus comma t minus double g by double x t minus t is equal to 1 upon p naught t. So, here, so it means that if you calculate the double g by double x here in this region minus double g by double x in this region, then it has the jump discontinuity of measure 1 upon p naught t. So, here double g by double x t plus t is defined as that limit x tending to t, where x is coming from the positive side of t, that is x is coming from this region. So, here your x is bigger than t. So, double g by double x t plus comma t is the derivative of double g by double x when x is reaching to this diagonal term, and double g by double x t minus t is when you reaching to towards the diagonal term from this region. Then this represent double g by double x t minus comma t is limit x tending to t when x is less than t double g by double x x comma t. So, here one is double g by g x t is continuous, another one is double g by double x is continuous in this triangle, and on the diagonal term it has a jump discontinuity and it is given by 1 upon p naught t. And next property is that for every element in alpha beta your zx gxt is a solution of the differential equation in each of the interval alpha t and t beta. So, it means that gxt is a solution of the differential equation in the region alpha t and t beta. So, at t it may not be a solution here. For every t in alpha beta zx equal to gxt satisfy the boundary condition. So, first of all it is the solution of the differential equation when t is not equal to x, and it satisfies the boundary condition which we have provided along with the equation. So, now let us now construct the Green function for self adjoint linear differential equation, and so let us consider the construction of Green function for a second order differential equation of the form p naught x y dash whole dash plus p 2 x y equal to 0, where p naught x is non-zero on this interval a b, and p naught x is basically a C1 function, means continuously differentiable function with the boundary condition that y of a equal to y of b equal to 0. So, basically it is a stem level problem which we are considering. So, it is a self adjoint problem and along with boundary condition we want to find out the Green function for this particular boundary value problem. So, let y1x be a solution of this equation 37 defined by the initial condition. We already know that if we have some initial condition, then this is a initial value problem and it must have a solution because your coefficients are continuous in this closed interval a b. So, by existence and uniqueness of initial value problem, this must have a solution. Let us denote that solution as y1x, and it satisfies the initial condition y1 a equal to 0 and y1 dash a equal to some alpha, where alpha is some non-zero value. So, this solution need not necessarily satisfy the second boundary condition, that is here y1b may not be 0, but if y1b is equal to 0, then we have already solved the our homogeneous problem, and we need not to consider about anything more. So, but here it may not always possible to have a solution for which y1b is not equal to 0, but any multiple of this y1 will have this property that c1 y1 x be a solution of this equation, that is Sturm-Liouville equation, and it also satisfies the initial condition, that is y1 y of a equal to 0. So, any multiple of y1 will have this particular property. Now, look at another solution y2x which satisfy the equation and the other boundary condition, that is y2b equal to 0. Here we can assume that y2 dash b is some non-zero value, so that it is not a trivial solution, because if we take y2b equal to 0 and y2 dash b equal to 0, then we have only a trivial solution of the homogeneous problem. So, here we assume that y2 dash b is non equal to 0, and the same condition will be satisfied by any multiple of y2. So, now we have propose our green function in the following form, that gxi equal to c1 y1 x for x defined from a to xi, and it is c2 y2 x when xi is from x to x is from xi to b. So, here we, if you look at this, you have x and you have xi here, and let us write it a to here, this is x equal to xi here. So, x from a to xi. So, from this here you have c1 y1 x, and here you have c2 y2 x, and you need to find out this c1 and c2 based on the properties of green function which we have assumed here. So, first property we have assumed that gxi is continuous at x equal to xi. So, on this diagonal it is continuous. So, it means that c1 y1 xi equal to c2 y2 xi. So, if we come from the left or the right, the value must be equal. So, c1 y1 xi equal to c2 y2 xi, because here we are approaching from this side and approaching from this side from at x equal to xi, it must be equal. So, c1 y1 xi equal to c2 y2 xi, that is from the continuity of gxt. Now, we also assume that dou g by dou x is continuous in triangle, but has a jump discontinuity at the diagonal term, that is x equal to xi here. So, here we simply say that dou g by dou x at say xi plus minus dou g by dou x at xi minus equal to 1 upon the coefficient term, that is p naught here. So, this is, so dou g by dou x when xi plus, so xi plus is this region, x is bigger than xi. So, it means that this represent the xi plus region. So, c2 y2 dash at point xi, so c2 y2 dash xi minus c1 y1 dash xi equal to 1 upon p naught xi here. So, we have these two conditions. Now, when you simplify these two things to find out c1 and c2, because if we know c1 and c2, then our green function is known to us. So, now we already have that rewriting the last two equation as a system of equation in c1 and c2. We observe that this Wronskian of y1 and y2, that is y1 y2 dash minus y2 y1 dash is basically Wronskian of y1 and y2 at the point x equal to xi is non-zero. Why? Because here your y1 and y2 are linearly independent solution. How we say that, if you look at, we have already assumed that ya equal to 0, but yb is not equal to 0, and we have, this is y1, and we have assumed our y2b is something which is satisfying 0 value at point B. So, y1b is non-zero, and but y2b is 0. So, from this we can say that y1 and y2 are linearly independent to each other. So, so it means that Wronskian is going to be non-zero, and let us call this Wronskian as w xi here, and with the help of this Wronskian we can find out c1 as y2 xi upon p naught xi w xi, and c2 as y1 xi upon p naught xi w xi. In fact, it is basically what you can write it here as these equations, you can write it here, that c1 c2 equal to here 0 and 1 upon p naught xi here, and here c1 c2 means you can write it here y1 xi and here it is minus y2 xi, here it is what minus y1 dash xi, here y2 dash xi. If we write down these two equation in terms of matrix equation Ax equal to b kind of thing. So, here from the first equation we can write y1 xi minus y2 xi c1 c2 equal to 0, and in last equation can be written in this term minus y1 dash xi c1 plus c2 y dash y2 dash xi equal to 1 upon p naught xi. So, we can write down these things in terms of this. Now, if you look at the determinant of this is basically the Wronskian of y1 and y2 at the point xi, and we have assumed that since y1 and y2 are linearly independent. So, this Wronskian is going to be non-zero throughout the interval. So, with the help of Wronskian we can write down the solution C1 and C2, and here we have to note down one thing, that this the denominator, this p naught xi w xi is going to be a constant value. For that we utilize the Lagrange's identity, and we note that y1 and y2 are solution of Ly equal to 0, and therefore from Lagrange's identity y1 p naught y2 dash minus y2 p naught y1 dash whole dash equal to d by dt p naught w y1 y2. Now, we already know that y1 y2 is basically a solution of this. So, this is going to be 0 here. So, we can write that p naught w y1 y2 is basically a constant value. So, p naught w y1 y2 at any point x equal to t, which I denote as wt, is going to be a constant value. So, that is what so if using this constant value I can write p naught w is equal to a. So, for all values of x. So, here whether you write p naught xi w xi or you simply write any constant a. So, here any constant means the value given at w at t. So, w at t is given as some constant. So, here either you write this or you simply replace this quantity by a constant a, where a is basically Wronskian of t at any point t in this interval a to b. Is that okay? So, gxi is now known to us. So, it satisfies all the properties of Green function, and moreover this also satisfies one very important property, that is gxi equal to g xi x. So, here when you interchange the rule of x and xi, then we have symmetricness. So, gxi is equal to g xi x. So, here it is a symmetric, and this symmetricity is coming from the fact that we are considering the self-adjoint second order linear differential equation. So, because of self-adjointness the Green function coming out to be a symmetric Green function. If we consider non self-adjoint or any type of equation, then this symmetricity may not be preserved. So, now here this is one some remark. The first remark is that solution y1 and y2 of equation 37 which we have chosen are linearly independent because we have assumed that y1b is not equal to 0 and y2b is equal to 0. So, that we have already noted down. Now, second remark which we wanted to note it here, that we have given the method of constructing the Green function for self-adjoint equation, but if it is not self-adjoint, then we have already discussed that how a given linear ordinary differential equation can be converted into a self-adjoint linear ordinary differential equation. And again I am repeating it, that if we have equation y double dash x plus p1x y dash x plus p2x y x equal to 0, here purposefully I am denoting the coefficient of y double dash x 1, and along with the boundary condition ya equal to a and yb equal to b. Here also I am assuming that we have a non-homogeneous boundary condition. So, first thing is that how to retain the self-adjointness of this equation, that we can do by multiplying a function e to power integration of p1x dx. If we multiply this, then this 44 can be converted into self-adjoint form. And now look at the non-homogeneous boundary condition, that can be rectified by a linear change of variable, that is if we assume zx equal to yx minus b minus a upon b minus a into x minus a, then this zx has a, in fact what we have done, here we have considered z of x equal to y of x plus ax plus b, sorry I have to use some other variable because a and b is already given here. So, let us assume this has say alpha and beta. Alpha beta I have not taken. So, here let us say that alpha x plus beta. We need to find out alpha beta such that z of a is equal to 0 and z of b is equal to 0. So, using this you can find out your alpha and beta. So, if you look at this is 0 equal to y of a is equal to a plus alpha a plus beta and b here beta here and z b is equal to 0. So, 0 equal to b plus alpha b plus beta. So, using this you can find out the value of alpha and beta here. That is what I have written here, that you can find out alpha beta and it is given by this. So, z of x equal to y of x minus b minus a upon capital B minus a divided by small b minus a x minus a minus a. So, if we use this, then we can change our boundary condition to homogeneous boundary condition, but if we do this then our problem will also change. So, problem is initially it is given as Ly equal to 0 is now changed to something like Lz equal to f of x. So, how we can look at here, Zx is given by this. So, you can write down z of x as y dash x minus some quantity, let us say this, into this is simply 1. So, you will get this quantity, that is b minus capital A divided by b minus a, and if you look at the z double dash x, then we have y double dash x. Is it okay? Then using these values, if you put it back, then what you will get? Let me write it here. So, your equation is basically what? Equation is this, y double dash plus p1x y dash plus p2x y equal to 0. I am just using the values of y double dash. So, y double dash is z double dash plus p1 x. Now, y dash is basically this. So, it is z dash plus p minus a upon small b minus a plus p2x, y is basically this, z of x minus b minus a small b minus a x minus a minus a is equal to 0. I think this will be plus here and this is plus here. So, here we have this, and if you simplify, what you will get? You will get here z double dash plus p1 x z dash x. So, this term we are taking and p2 plus p2x z of x, and what left we are shifting it there. So, here we have this quantity. First thing is this, that p2x, when you shift it there, then we have a negative sign. So, here p2 and within bracket we have p minus a divided by small b minus a x minus a minus, so this is minus a right. So, we are taking this term along with these two terms. So, minus p2 into within bracket what you have, and minus p1x, we are considering now this term p1x and b minus a upon small b minus a. So, that is what we have written here. So, it means that now our problem is, so this is what, this is Lz and we call this quantity as some function of x. So, now by changing the non-homogeneous boundary condition to homogeneous boundary condition, we have used this transformation, but this transformation changed the boundary condition to homogeneous boundary condition, but it also changed the homogeneous equation to a non-homogeneous equation. So, here what we have done is that we have considered the homogeneous equation with non-homogeneous boundary condition. When we do this change, then we have non-homogeneous equation with homogeneous boundary condition. That is what we have seen here. So, now we should know how to solve this non-homogeneous equation with homogeneous boundary condition. Okay. So now let us consider one simple example based on whatever we have just presented. So find the green function of the problem y double dash plus y equal to 0 with the boundary condition y 0 equal to y pi by 2 equal to 0, and then we want to solve the non-homogeneous problem, that is y double dash plus y equal to 1 plus x, and non-homogeneous boundary condition as well, that is y 0 equal to 1 and y pi by 2 equal to 1. So we start with homogeneous problem, and with the help of green function we try to solve the non-homogeneous equation along with non-homogeneous boundary condition here. So first let us first find out the green function. So to find out the green function we have to look at the homogeneous equation along with homogeneous boundary condition, and if you solve that we have yx equal to c naught cos of x plus c1 sin of x, and if you look at these boundary condition, then y 0 equal to 0 equal to y pi by 2 equal to 0, we have only a trivial solution. So it means that homogeneous problem with homogeneous boundary condition has only a trivial solution. So by the first theorem which we have discussed in the beginning of the lecture, that in this case we have green function exist, and with the help of green function we can solve the non-homogeneous problem. Okay. So first we have green function exists, and now we want to find out the green function. Now please note down here that the homogeneous equation is given in self adjoint form. So we can easily find out the gxt with the procedure we have already discussed. So gxt equal to a cos x plus b sin x, where x is lying less than or equal to t, look at this term only, and c cos x plus d sin t when t is less than or equal to x. So we have two reasons, x less than or equal to t and t greater than or equal to x. So here we need to fix your a b c d depending on the properties of this. So here first here that this a cos x plus b sin x must satisfy the boundary condition given at the point x equal to 0, and c cos x plus d sin x satisfy the boundary condition given at the point x equal to pi by 2. So here we already know that for each t from 0 to pi by 2, yx equal to gxt is a solution of the differential equation and satisfy the boundary condition. So y 0 equal to 0 implies that a equal to 0, and y pi by 2 equal to 0 implies that t equal to 0. So here if you look at the that in this domain your x equal to 0 is coming, so the gxt will satisfy the boundary condition at x equal to 0 by this function, and gxt will satisfy the other boundary condition defined at pi by 2 by this function. So it means that you can find out that y of 0 equal to 0 implies that a equal to 0, because this is the solution which contain the reason x equal to 0. So here we will get a equal to 0, and similarly y pi by 2 equal to 0 means your d equal to 0. So our gxt is now reduced to this, that is gxt is equal to b sin x when x is lying between 0 to t, and c cos x when lying between t to pi by 2. So now we have to find out this b and c. So what we have utilized so far, we have utilized so far that gxt is a solution of the differential equation. So with the help of this we have constructed our gxt, and that gxt satisfies the boundary condition. So with the help of boundary condition we have fixed our a and one of the constant. Now let us fix the other remaining constant b and c, and for that we have two condition, that gxt is continuous and gxt has a jump discontinuity. So let us say that since green function is continuous on 0 to pi by 2, so let us check the continuity at x equal to t. So it means that if we come from this region or this region we will get the same value. So b sin t has to be equal to c cos t, and then other condition, that is it has a jump discontinuity. So it means that dever g by dever x from t plus to minus t minus equal to 1 upon pt. So if you look at dever g by dever x from t plus, so t plus is this. So here you can say that minus c sin of t, we are looking at x equal to t, minus b cos of t equal to 1 upon pt, pt is basically 1 here, so it is 1. So we can simplify this and we can write c sin t plus b cos t equal to minus 1, this minus we are shifting here. So we have for equation 49 and equation 50, and with the help of this we can find out the constant b and c. So when we find out the constant b and c, it is coming out to minus cos t and minus sin t, and with the help of bc now we are able to write down the green function, that is gxt is minus cos t sin x from 0 to t and minus sin t cos x when t is from x is from t to pi by 2, and you can see that your symmetricity is preserved here. So it means that gxt can be replaced by gtx. Anyway, so now let us fix the boundary condition as well. So we have not fixed the boundary condition. So for fixing the boundary condition, so let us assume that zx equal to yx minus 1. In fact, you can assume zx as yx plus alpha x plus beta, and you can simplify u alpha and beta, and it is coming out that alpha is coming out to be 0 and beta is equal to minus 1. So zx equal to yx minus 1. Now with the help of this, now reduce your non-homogeneous problem, that is y double dash plus y equal to 1 plus x and these boundary. So these boundary condition is already fixed. Now z of 0 equal to 0 and z of pi by 2 equal to 0, and you if you fix this, then you have z double dash plus z equal to x, and with this now if you look at, we have homogeneous boundary condition and a non-homogeneous equation, and we already know that the solution is given by z of x if from 0 to pi by 2 gxt into ft dt, where ft represent the right hand side of this equation, and here your x ft is basically t. So z of x is equal to 0 to pi by 2 gxt into t dt. Now here depending on the domain you have to use different values of gxt. So you can simply write it 0 to t gxt t dt plus t to pi by 2 gxt into t dt. So we have to look at that in this region when here sorry, yeah, here if you look at I have to write 0 to x. So let me write it here 0 to x here. So here 0 to x and x to pi by 2. So here you look at that t is less than or equal to x. So in this way t can go up to x. So t less than or equal to x means x is greater than t. So if you look at in x greater than t means minus sin t cos of x. So here we use minus sin t cos of x. So here we are using this value. So gxt is minus sin t cos of x, we are using it, and here in this way your t is bigger than x. So t is bigger than x means t is bigger than x means minus cos t sin of x. So this will be used here. So here we use this part minus cos t sin x. So minus cos t will go outside and sin x is taken outside because integral is with respect to t. When you simplify, you will get your solution zx equal to x minus pi by 2 sin of x. I am not doing this integration because it is a simple integration, you can do it. So once we have z of x, then since we already know zx is yx minus 1, so we can have our solution of the problem, that is yx equal to 1 plus x minus pi by 2 sin x, and this is the solution of this problem y double dash plus y equal to 1 plus x condition y 0 equal to 1 and y pi by 2 equal to 1. So what we have seen in this example, how to construct a green function, and with the help of green function how to solve a non-homogeneous equation with non-homogeneous boundary value problem. So here I will conclude our lecture, and next lecture we will discuss some more result on green function and discuss some more example based on this. So thank you for listening. Thank you.